So in order to understand the working of the AC machines, the first and foremost concept that you need to know is the rotating magnetic field. A magnetic field that is rotating. So this is usually abbreviated as RMF. Okay. So we will start off with how this RMF is produced. Okay. Now if you take a current wire, it is carrying a current I, then what will be the direction of magnetic field that will be produced? It will be concentric to this current carrying conductor. What about the direction? You have to wrap your right hand fingers around the wire in such a way that your thumb is pointing in the direction of current. Then your fingers will wrap around in this direction, right? So this is the direction of the magnetic field. So now this is a straight current carrying conductor. What if you are taking a coil? This is a rectangular coil. Okay. Now the current is flowing through this terminal and it is coming out through this terminal. Okay. Now each of the conductors, if you take, okay, so this is one conductor, this is one conductor, this is one conductor, and this is another conductor. So each of the conductors, if you take and you find out the magnetic field direction, okay, for this it is going to be in this manner. For this it is going to be in this direction. Similarly for this side of the conductor, the magnetic field is going to be in this direction. For this conductor it is going to be in this direction. Okay. So now what will be the equivalent magnetic field of this entire coil? For the straight conductor, concentric circles. What about for a coil? So if you draw the coil on the plane of this screen, let us say, okay, the coil is in the plane of this screen. Now the current is going in this direction, so it is, you can say, in the clockwise direction. So now the magnetic field direction will be going into the plane. This is for the point that is internal to the coil itself. Okay. Similarly, we are not talking about the external points, we are talking only about the points that are internal to the coil, that is inside the coil. Okay. So similarly, if you take the current in opposite direction, so that means this is the direction of current. It is entering here and coming out of here. Here it is entering here, coming out of here. Okay. So then what will be the direction of magnetic field? It is going to be coming out of the plane. This direction is also, it is very easy to check. It is easy to verify. So how you can verify is, you take your right hand, just in the case of the straight conductor, you take your right hand and you wrap your fingers in a direction such that the thumb is pointing to the direction of magnetic field in this case. Okay, here we pointed the thumb in the direction of current. Here we are pointing the thumb in the direction of magnetic field. Okay, so in that case you will see that your fingers will wrap around in a clockwise sense. Okay, similarly here, if you wrap your fingers in a direction such that your thumb is pointing upward, then your fingers will wrap in the counterclockwise sense. Okay, so this is how you can verify whether the direction that you actually got here of the magnetic field, whether it is true or not. Okay, so that is the difference between a straight current carrying conductor and a coil, a current carrying coil. So this is some of the basic concepts. Now you take a machine, the stator of a machine. Okay, and for this stator, let us take rotor slots here. Okay, so that means we can place the conductors here, the coils. Okay, so the coils we will mark with red. So this is one coil and this is other side of the same coil. That means if this is the coil, okay, we are seeing from this end, the top view. Okay, so if the current is flowing in this direction, on one conductor current is flowing in the upward direction, so let us take it to be outward. Okay, and on the other side then current will be going into the plane. Okay, now what will be the direction of magnetic field for this coil? So if you apply the right hand rule, you will get that the direction of magnetic field in the interior is going to be in this direction. Okay, so this is the magnetic field B bar. H bar, that is the magnetic field intensity, will also be in the same direction because B bar is equal to mu into H bar, right? So if you are wrapping your fingers such that your right hand thumb is pointing in this direction, then your fingers will wrap around in this direction. This is the direction of current you will get. Okay. Now in order to get a rotating magnetic field RMF, we will need 3 coils. We will make use of 3 coils. Okay. So one of the coils is placed here. The other 2 coils we have to place in such a way that all the 3 are spaced at 120 degrees from each other. So that means this is the top end of the coil, right? We can see this line. Now the other coil will be 120 degrees. This angle here is 120 degrees. Okay. And similarly, you can get another coil at 120 degrees like this. Okay. So you can make rotor slots here. Okay. So we can place the coils. Here there will be one coil. In each of the slots we are going to place coils. Okay. Now what is the direction of current? If you consider this to be coil A, okay, one side we will take as A, the other side we can take as A dash. Okay. Now after 120 degrees from A will be this coil, right? So this coil we will take as B. Now this will also have the same current direction, that is current that is coming out of the plane. So this is going to be B. The opposite end is B dash. Here the current will be going into the plane. Okay, you can see that A dash and B dash, they are 120 degrees apart. Okay. Next, after 120 degrees more, that means this is B. After 120 degrees more, you have a coil here. So here you are going to get C. The current is coming out of the plane. And the other end of the coil will have current going into the plane. So this we will name as C dash. Okay, so here we have a set of 3 coils. You can write down here set of 3 windings which are placed 120 degrees apart from each other. Okay. Now, next what you have to do, in each of the 3 coils you have to send currents in such a way that the 3 currents are 120 degrees apart with respect to time. Okay. So we will understand it. Don't worry if it's confusing. Each winding should carry current of equal magnitude but with a phase shift of 120 degrees. Okay, so that means 3 phase balanced currents should flow in the windings. Okay, one current for one phase for each winding. So in the first point we are talking about this 120 degrees apart is with respect to spatial difference, and this is with respect to time. Okay, 120 degrees apart spatially, 120 degrees apart with respect to time. Understand the difference. Okay, let us now see what will be the equivalent magnetic field that we can get when we are using this type of setup. Okay, so here you have the coils, once again same as it is, just like in the previous case, right? Here you have the coils. We will name them as, this is A, current is coming out. Here this is A dash. This is going to be B, current is coming out. This is B dash. This is C, C dash. Now for A dash, what will be the magnetic field direction? It will be in this direction. This is a vertical line. Okay, so this is going to be perpendicular. This is, we will name as H A bar, the magnetic field intensity. Okay, now what about for the coil B dash? For this also it will be perpendicular. Now this is 120 degrees with respect to this line. You can draw, in fact, this is A dash coil, this is B dash. Now this angle is 120 degrees. Okay, so now H bar is coming from here. This is going to be perpendicular to the B dash coil. Okay, so what is this magnetic field intensity? It is HB bar. Now what will be this angle? It is going to be 120 degrees. Similarly, for this coil CC dash. Once again you can draw the coil here, line joining these two. So now the magnetic field is going to be perpendicular to this coil. So this is HC dash. Okay. So if you just redraw the magnetic field separately, then you're going to get this is HA bar, this is HB bar, and this is HC bar. Okay. So you can see that spatially with respect to space, HA bar is in this direction, HB bar is in this direction, HC bar is in this direction. Okay. Now in addition, what is happening? The HA bar, if you take it, is produced by the current flowing through the coil A, and HB bar is produced due to the current flowing in coil B. Now A and B, the currents between A and B have a phase shift of how much? 120 degrees. So similarly, HA and HB will also be at a phase shift of 120 degrees, right? Because HA will be in phase with current through coil A. Okay, you can write AA dash. Similarly, HB and HC. Okay, so HB will be in phase with current through coil B dash. HC will be in phase with current through coil C dash. So what you will do now, IA current or IAA dash, let us take it as IM sine omega t. So that means it is having a magnitude IM and the initial phase is 0. IBB dash, now what will this be? We are taking 3-phase balanced currents. So the magnitude will be IM, whereas the phase will be 120 degrees lagging. Okay, sine omega t minus 120 degrees. And ICC dash, so is going to be same magnitude, sine omega t, another 120 degrees lag. So minus 240 degrees, or you can also write this as what? IM sine omega t plus 120 degrees. Lagging by 240 degrees or leading by 120 degrees is one and the same. So from here you can get HA bar. This will be having some magnitude HM. Okay, the magnitude is, for now it is not important to us. It will have some magnitude HM, and the phase is going to be same as IA dash, which is 0 initial phase. Okay. Now what about the spatial consideration? We saw that this is HA, this is HB, and this is HC. Okay. So now if you take the Cartesian plane, this is X and Y. Okay. So how can we represent this HA bar vector? We can represent it with its magnitude, which is HM sine omega t at any point of time. This is the magnitude, and the direction you can write as I cap, right? Now what about HB bar? HB bar will be having the same magnitude HM as HA, but the phase will be 120 degrees lagging. Okay, same phase as this current, the current through coil B. Okay, now what about the space? Here HB bar is here, right? Now what is the angle? This angle is 120 degrees, so that means this angle is 60 degrees. So we can resolve into horizontal and vertical component. So what will be the horizontal component? It is going to be minus HB cos 60, and vertical component will be minus HB sine 60, or you can write cos 30. So HB, if you take out common, you are going to be left out with minus cos 60 I cap minus sine 60 j cap. Okay. Next, finally, HC bar you can write as same magnitude HM. Now what will be the phase? The phase you can write as plus 120 degrees or minus 240 degrees. Okay. Then how do we represent the spatial factor? For HC here, the component on the horizontal component is 60 degrees. So you're going to be having minus cos 60 I cap plus sine 60 j cap. Now we can find out the net magnetic field intensity. So you can write H net. This will be equal to HA bar plus HB bar plus HC bar. Okay. So now you keep all of the I components on one side. So what are you getting? Hm sine omega t, and then here HB I component is minus cos 60 Hm sine omega t minus 120 degrees. So this is minus 0.5 Hm sine omega t minus 120 degrees. Okay. And finally in HC component, the I component is once again minus cos 60 Hm. So minus 0.5 Hm sine omega t plus 120 degrees. Okay. So this will be the I component. Similarly, you will write the horizontal components of HA, HB and HC. HA does not have any vertical component. So you are going to have minus sine 60 is minus root 3 by 2 Hm sine omega t minus 120 degrees plus sine 60, that means plus root 3 by 2 Hm sine omega t plus 120 degrees. Okay. So this is going to be the J component. So now use the trigonometric identities. Sine A minus B is sine A cos B minus cos A sine B, right? So what will be sine omega t minus 120 degrees? This is going to be sine omega t cos 120 degrees minus cos omega t sine 120 degrees. What about sine A plus B? Just here positive sign will come. Okay. So sine omega t plus 120 degrees is going to be sine omega t cos 120 degrees plus cos omega t sine 120 degrees. Okay. So you apply the same thing here. So what are you going to get here? This term you are going to be left out with Hm, you can take out common. So you are going to be having sine omega t minus 0.5 you can take out common. So you are going to be left out with sine omega t minus 120 degrees plus sine omega t plus 120 degrees. So this is I cap. Okay. Similarly, next you can take out root 3 by 2 Hm common. So plus root 3 by 2 Hm, you are going to have minus sine omega t minus 120 degrees plus sine omega t plus 120 degrees. This is J cap. Okay. So now you can add these two here in this case. So what are you going to be left out with? This is equal to Hm sine omega t will remain as it is minus 0.5. If you add these two, this part and this part will get cancelled. So 2 times sine omega t into cos 120 degrees. Okay. So into 2 times sine omega t into cos 120 is minus 1 by 2. Okay. So you can write minus 0.5. This is I cap. Next, what about the vertical component? You are going to have plus root 3 by 2 Hm. Similarly, you are going to get here 2 times cos omega t into sine 120. Sine 120 is root 3 by 2. This is J cap. So finally, you are going to get here sine omega t plus 0.5 sine omega t. So what will it be? 1.5 sine omega t. So you can write 1.5 Hm sine omega t I cap. Now similarly here what you are going to get? 3 by 2, that is same as 1.5. So 1.5 Hm cos omega t J cap. Now this is in terms of the horizontal and vertical components, right? If you can write in magnitude phase form, then what are you going to get? Or magnitude will be root over 1.5 Hm sine omega t square plus 1.5 Hm cos omega t whole square, right? So this if you find out, you are going to get 1.5 Hm, right? Because sine omega t, sine square omega t plus cos square omega t is simply 1. So you can write the magnitude is 1.5 Hm. And what about the phase? The phase is going to be tan inverse cos omega t divided by sine omega t. 1.5 Hm will be cancelled, right? So this, if you see, you can get tan inverse cot omega t. Cot omega t you can write as tan of 90 minus omega t. Finally, you are going to get 90 minus omega t. Okay. So angle 90 minus omega t. So that means the magnitude is remaining constant while the phase is changing with respect to time. So this is the important part, because this is where you will see that you are getting a rotating magnetic field. Okay, magnetic field which is rotating. If you substitute various values of time, then you will understand better. Consider the time t is equal to 0, okay, or omega t is equal to 0 degrees. Then what will be the magnetic field? Just have to substitute omega t is equal to 0. You are going to get 1.5 hm angle 90 degrees. So that means it will be at 90 degrees with a magnitude of 1.5 hm. Okay. So this angle is 90 degrees. Now what about at pi by 2? Okay. So when t is equal to pi by 2 omega, that is the time. At this time instant, h net is going to have 1.5 hm as it is. 90 minus 90 will be 0 degrees. So that means it will now be in this direction. So 1.5 hm bar, angle 0. Next instant of time we will take omega t is equal to pi. So at omega t is equal to pi, then what is going to happen? H net is, magnitude will once again remain same. Angle will be 90 degrees is pi by 2. So pi by 2 minus pi. What will it be? Minus pi by 2, or you can write minus 90 degrees. Okay. So now what will be that? This will be the reference. Minus 90 degrees will be in this direction. Magnitude is once again remaining same. Okay. Similarly, you can see that for omega t is equal to 3 pi by 2. The angle will be here. Okay. So the vector, you can see effectively it is rotating in the clockwise sense, while the magnitude is remaining the same. So initially it was here, then it has come here, then it has come here. Okay. So it is going in the clockwise sense. This is how you are getting a rotating magnetic field with the help of 3-phase balanced currents. Okay. So please write it down once again. You are making use of 3-phase balanced current. So that means 120 degrees shift with respect to time, and windings 120 degrees apart. That means with respect to space. When these two are happening, then you will get a rotating magnetic field. This is the basis for an induction machine as well as a synchronous machine. So make sure you understand this properly. Okay. So we have seen how 3-phase currents can be used to create a rotating magnetic field, right? Now when you have a rotating magnetic field and you have 3 windings which are 120 degrees out of phase, then you can induce 3-phase balanced currents in them. Okay, so it works both ways. Using 3-phase balanced currents, we can produce an RMF, and using, if there is an existing RMF, then this RMF will lead to a 3-phase current. Okay, so this is the basic point that you need to know if you have to understand the working of AC machines. What are the 2 AC machines that we are going to study? Induction machines and synchronous machines. Both of them will make use of the rotating magnetic field. And in the induction machine you will have motor and generator. In synchronous machine also you will have motor and generator.